I'm happy to see so many of you here this afternoon, this hot afternoon. Seeing a lot of familiar faces as well, so welcome all. On behalf of VONK, I'm hosting this presentation on how to optimize the electrolyzer power supply for the electrical grid of tomorrow. We'll explain not only a bit on the experience that we have from multiple projects that we've done over the years in this business, and the things that we see in trends of trying to reduce OPEX, CAPEX and floor space, but also in the grid requirements that are playing an ever more important role in the execution of projects. So, my name is Bart Vries, being the commercial lead at VONK and therefore hosting this presentation. I'll quickly to the agenda. As I mentioned, I will focus a bit on what actually are the power supplies that we're looking at today, the grid requirements, a couple of scenarios in how this comes to life when choosing the right type of power supply, and obviously having a recap afterwards. For those of you who are not familiar with VONK yet, so VONK has more than 80 years of heritage in various industries, but we're now fully focused on the energy transition. That's not just in green hydrogen, but it's also in decarbonization of oil and gas, and for instance in the uranium enrichment industry. This is something that we do on a global basis. So we're based in the Netherlands, but we are a company with global reach. To give you a couple of examples, short examples, because I want to focus on the content. In the uranium enrichment industry, a highly demanding industry, we are by far and away the biggest supplier of power conversion equipment in the world. And if you look at our legacy already, our proof of our merits in the hydrogen business, we have done Sunfire's biggest project. This one is in Finland, and we are now executing the biggest project of another OEM as well in Europe, which is also coincidentally the biggest project executed in Belgium. So what is it that we provide? Well, here's a nice picture of a rectifier that we built. And you may have seen the brand NEA, because that's how we brand our power supply specifically for the hydrogen business. So what is it? If we look at the ecosystem of an electrolyzer, basically you have on one side the electricity grid, the source of our electricity. On the other side there is the electrolyzer, and our power supplies are in between, which makes us more or less an interface. And this is an interface between the electricity grid with its complications. And we see, and taking this example from the Netherlands, but it's generally applicable in Europe, we see the electricity grid as a means to transport electricity from the source of generation to the location of its consumption, which means that you are depending on the generation of electricity, and if this is green, you're depending on wind characteristics, solar characteristics, and the location at which these are generated. And when it comes to consumption, you are depending on where it's consumed and how much it's consumed. And obviously, big electrolyzers are having a very big impact on the electricity grid in terms of their consumption. And that means to lack of availability in the electricity grid, which is hard to scale up for the electrical grid operators. Therefore, what we see happening more and more happening is that they are using a number of measures to tighten the requirements, or basically to free up capacity in their electricity grid, or to reduce their own problems. And a lot of them are actually applicable when it comes to electrolyzers. I will mainly focus on tightening the power quality requirements, and especially on when it comes to harmonics and power factor. And that will be reviewed in the next couple of slides, but it also has to do with improving actually the power factor levels of the electricity grid, as well as having fault right-through capabilities. The italic one is a very clear one, because it involves how you operate an electrolyzer, but as such it doesn't have a direct impact on how we have to set up a power supply, because it goes with the flow. So to explain these items in a bit more detail, one of the big topics of attention is power factor. And I won't go too technical, but we get a lot of questions on and variation in demands ranging from basically 0.9 to 1. And what it means that if you have a bad power factor, or you have more capacitive or inductive elements that are causing a load to the grid, and a bad power factor basically leads to, if you have a 0.9 level, 11% more load on all the components in your grid compared to a perfect power factor of 1. So it's having a big impact on existing or even future installations. If you look at harmonics, basically what you want in your electricity is a perfect sine wave, because then you have no interruption whatsoever. But it's not a fact of life. In practice, every electricity grid has consumption. So it doesn't go like this. There's always some kind of fluctuation involved. And it's a weighted average. So everything that you put on it that is big is having a bigger impact on the overall performance. But it doesn't mean that adding something big is necessarily a negative thing. If you actually connect a big consuming user to an electricity grid, like a big electrolysis plant, you can actually improve the overall grid characteristics of the grid to which it is connected. Now I've got a small example. I won't go into too much details, but if you connect a 100 megawatt plant to a grid that's already having a load of 1 gigawatt, its influence is relatively minor. But if you are connecting a gigawatt plant to a gigawatt of existing load, then you can imagine that it's going to have a big impact, either positively or negatively, and that definitely will impact the choices that the grid operator makes with the requirements they set out to certain projects. So why is this important? All these kind of things with grid requirements and the power factor and the harmonics. It is important because it reflects into the choices that you have to make with your power supply. There are different types of technology that you can apply with your power supply, and all of them have different characteristics when it comes to power quality, to scalability in terms of current and voltage, as well obviously into pricing. And this means that in different circumstances, with different electrolyzers, different types of rectifiers in our case, will be the most commercially viable option compared to other cases. And I have a couple of scenarios which I want to show to you to illustrate this. So this is the first scenario. If you have what we call a typical alkaline electrolyzer, they are roughly within the ballpark mostly of an end-of-life voltage, the highest voltage level of 500 to 800 volts, and current levels up to 10,000 amps. And then if you take grid requirements that you quite often see in Spain or France, what we see is that the grid requirements are relatively moderate. There is a relatively low voltage. This means you don't need a full IGBT solution because that's very good on power quality, which is not necessary, and it's a bit more expensive once the voltage is lower. So that's out of the window. So then we have two alternatives that could be viable, which is a diode chopper or a thyristor type of setup. And the thing is, a thyristor converter is basically as a base converter cheaper, but you need additional equipment to be compliant to the power quality requirements. And this additional equipment is more expensive than the gap in initial pricing. So therefore, this diode chopper overall for this kind of setup is the cheapest one. And it's illustrated as a couple of the projects that I've shown are actually implemented with this diode chopper setup for such type of electrolyzers. And this was, I mean, we've done this business, so we were commercially the most attractive. That's the reason why. If you take this reasoning to the extreme end, and you take the same kind of power quality requirements, but you increase the current level to an extreme end, there's actually only one manufacturer of electrolyzers who is in this ballpark, then basically all the way to the bottom you follow the same type of reasoning, but then because of this very high current, this suits the thyristor very well, the price gap between a thyristor and any other technology is so big that the cost of fixing the power quality deficits is less than the price gap in the rectifier itself. Therefore, you go with a thyristor setup. Then moving to the entire other end of the spectrum is where you have very tight grid requirements. And this is something that we already see in the Netherlands and in Denmark, for instance, but also in Belgium. And if we link this to a typical PEM electrolyzer, which has a higher voltage point, but therefore a lower current level, did you see that just because of the grid requirements, you don't even need the diode chopper or thyristor of the previous examples is already out of the question. So you need to go full IGBT to solve the grid requirement troubles. Then is the question, do you need a single stage or a two-stage conversion? And given the electrical characteristics of this electrolyzer setup, you need a single stage. It's the most attractive solution for this particular electrolyzer. And basically, to quickly go back to this example, we can offer these topologies all at once because we are not fixed to a certain standard that we have to take from our existing product portfolio. We've specifically designed this type of topologies for this electrolysis application in a standardized setup. And working with this standardized setup, we've already had a lot of business, which means that our NEA rectifiers are competitive and suitable for this application. But it's not enough. As I mentioned, we are in a market active where the market not only wants us to improve on OPEX and CAPEX because we need to make the business case viable, but we also want to reduce footprints. We want to have better integrated packaging in the overall electrolyzer plant setups, which means we want to use less copper. And obviously, if we want to produce them in really massive numbers, we need to increase the manufacturability of these solutions, which means the solution as we have it today, which is already successful, is not the solution that we want for ourselves for tomorrow. We want to improve on that. And therefore, I can announce you today that we are very far advanced in the development of a new generation of NEA rectifiers, which is going to be a lot smaller, and I can promise you that it's having a footprint decrease of more than 25%, making it by far the smallest electrolyzer in power supply in its area. And it will make a difference for a lot of projects in the execution. So, to wrap up, this power supply is an interface. And as it is an interface between the dynamic elements of the electrolyzer with its various characteristics and the various grid requirements that we face in the different projects over the different locations, you really need to be careful to select the right type of topology, the right type of electrolyzer, and not being stuck to either a full IGBT for everything, because that doesn't work, or either a thyristor for everything, because that doesn't work. You need to have the fitting type of power supply for a specific electrolyzer and grid requirements type of combination. And therefore, it is key to have early involvement. You don't want to get stuck with something that doesn't fit afterwards, either because you have over-dimensioned it and you pay too much, or you have under-dimensioned it and you have to solve something in practice by adding additional equipment, which you don't want because it's not incalculated in your pricing and not incorporated in your floor plan. So that's something that you want to avoid, and that's a strong message that I would like to give to you. And we are happy to be part of this early involvement, to be able to ask the right questions and to provide you with the right solutions. So thank you for your attention. I think with a half minute spare, there is maybe time for one single question. I'm looking at Celine. No, it's not. Okay, thanks, Celine. I will keep it short then. And then, well, thank you for your attention. We are at booth A78, so it's at the entrance of Hall 3, and looking forward to see you afterwards. Thank you very much.